For decades, the rules of modern warfare have been built on a simple equation: fire a missile to destroy a missile. But what happens when the cost of defending yourself is 1,000 times more expensive than the cost of attacking in today's video? We're going to show you why the United Kingdom may have just broken that equation forever. With Dragonfire, a laser weapon that can destroy incoming threats for roughly $13 a shot, and why this technology could mark the beginning of the end for traditional missile defense as we know it, because when you can fire an invisible beam of light at the speed of light with an infinite magazine and a cost per shot less than a cup of coffee in London, the entire calculus of war changes. To appreciate why Dragonfire matters so much, we first need to understand the problem it was built to solve, and that problem has a name. The cost-exchange ratio. For the last several years, Western navies have been trapped in what defense analysts describe as an economic death spiral, using multi-million-dollar interceptors to shoot down threats that cost less than a used car. The most dramatic example of this crisis has been playing out in the Red Sea since October of 2023, where Houthi rebels armed with Iranian-supplied drones and missiles have been attacking commercial shipping and forcing U.S. Navy destroyers to burn through their most sophisticated weapons at an alarming rate. The Samad series drones used by the Houthis cost between $15,000 and $30,000, the Shahed 136 variants between $20,000 and $50,000, and some modified commercial drones cost as little as $2,000. Meanwhile, the missiles used to shoot them down tell a very different story. A single SM-2 standard missile costs $2.1 million. The SM-6 runs between $4.3 and $9.5 million, depending on the variant. Even the evolved Sea Sparrow comes in at $1.5 million each. The numbers are staggering. Between October 2023 and mid-2025, the U.S. Navy expended over 700 standard missiles in Red Sea and related operations at a total munitions cost exceeding $1.8 billion. And the most unsettling part of that figure is what it was spent destroying. In many engagements, the U.S. Navy was spending $2 million to neutralize a $20,000 drone, a cost ratio of 100 to 1. And in some cases, when SM-6 missiles were used against the cheapest commercial drones, the ratio exceeded 1,000 to 1. This is not a sustainable model of warfare, and everyone from the Pentagon to Parliament knows it. This is where Dragonfire enters the picture, developed by a British consortium led by MBDA UK, with Leonardo UK providing the beam director and Chinetti Q supplying the phase-combined fiber laser source. Dragonfire represents a fundamentally different approach to air defense. Instead of launching a physical projectile that costs millions and cannot be recovered, it fires a concentrated beam of light that costs approximately 10 pounds, roughly $13 in electricity per shot for the cost of a single SM-6 missile. You could theoretically fire over 330,000 Dragonfire laser shots. And unlike a missile magazine that runs dry after 96 shots from a destroyer's vertical launch system, a laser weapon has what the military calls a deep magazine. It can fire indefinitely as long as the ship's engines are generating power. But the question everyone asks is, does it actually work? The answer came on January 19, 2024, at the Ministry of Defense Hebrides Range in Scotland, where Dragonfire conducted its first high-power aerial engagement test, and the results were nothing short of impressive. The system successfully shot down multiple drones, including high-speed targets traveling at over 400 miles per hour, and it demonstrated a level of precision that borders on the absurd. Dragonfire can hit a target the size of a 1-pound coin, approximately 23 millimeters in diameter, from a distance of 1 kilometer. The system operates in the 50-kilowatt power class, with the UK MOD already exploring a scale-up to 150 kilowatts for future frigate integration. And unlike a missile, which you fire and forget, a laser tracks its target using an electro-optical camera system and a secondary low-power laser for precision pointing before unleashing the high-energy burst. Speaking of how it actually destroys targets, this is where the physics gets fascinating. A high-energy laser doesn't explode anything. It transfers intense concentrated heat to a specific point on the target in a process called thermal loading. The laser heats the target's surface material until it melts or structurally weakens. And when that target is a drone moving at 400 miles per hour, a weakened wing spar or control surface will snap under aerodynamic forces in seconds. Alternatively, if the beam contacts the fuel tank or the explosive warhead directly, it can cause a catastrophic secondary explosion. Typical engagement requires between 10 and 20 seconds of sustained contact, what the military calls dwell time. Now, the deployment timeline for Dragonfire has been aggressive by defense procurement standards. The system was originally slated for integration by 2032, but former Defense Secretary Grant Shapps pushed for acceleration, stating in April 2024 that he wanted to speed up what would usually be a very lengthy development to a much shorter time frame, possibly in order for Ukrainians perhaps to get their hands on it. The current target is initial deployment by 2027 on a Type 45 Daring-class destroyer, with subsequent integration planned for the Type 26 and Type 31 frigates via modular mission bays. But Dragonfire is not alone in this revolution. Directed energy weapons are emerging across every major military power. Israel's Iron Beam operates at 100 kilowatts and has entered operational testing as a complement to the Iron Dome. The U.S. Navy has already deployed Helios, a 60-kilowatt laser system aboard the USS Preble. An Arleigh Burke-class destroyer, the U.S. Army's DEM Shored, mounts a 50-kilowatt laser on a Stryker fighting vehicle, and Lockheed Martin's IFPCHEL is pushing toward an extraordinary 300 kilowatts for the Army's integrated air defense mission. The race is on, and the United Kingdom is positioning itself at the front. Of course, it would be irresponsible to suggest that lasers are a perfect solution. They are not, and the limitations are real. Rain, fog, dust, and smoke scatter the beam, reducing effective range significantly. A laser that kills at 5 kilometers in clear air may struggle to reach 1 kilometer in heavy fog. There is the problem of thermal blooming, where the beam heats the air. It travels through, creating a lens effect that defocuses the energy, and because a laser must maintain contact with its target for several seconds, it is vulnerable to saturation attacks from drone swarms, where multiple threats arrive simultaneously, overwhelming the tracking system's ability to engage them sequentially. Reflective mirror coatings and ablative materials that flake away to dissipate heat can also increase the time required for a kill. But here's the kicker. These limitations apply to the current generation. The trajectory of laser weapons technology mirrors what happened with early radar or early jet engines. The first versions are always limited. The second and third generations are where the transformation happens, and it's worth remembering how far this technology has come. The last serious attempt at an operational laser weapon was the YAL-1 airborne laser, a modified Boeing 747 that carried a massive chemical laser in its nose. The program cost over $5 billion and was ultimately canceled because the chemical fuel was toxic and heavy, and the range was insufficient. The difference between that failed experiment and Dragonfire is the same difference between a vacuum tube computer and a smartphone. Modern directed energy weapons use solid-state and fiber optic laser technology derived from commercial telecommunications equipment. The same technology that powers high-speed internet cables now powers weapons that can knock drones out of the sky for $13. The implications are profound if laser weapons scale as expected, and current development trajectories suggest they will. The entire economic model of missile-based air defense begins to collapse. Why would any navy spend billions on missile magazines when a laser offers unlimited shots at negligible cost? Why would any air force invest in standoff missiles when directed energy can neutralize them at the speed of light? The Red Sea crisis has proven beyond any doubt that the old model is broken, and Dragonfire may be the first credible answer to what comes next. So what do you think? Will directed energy weapons truly replace traditional missiles in the next decade, or are lasers still too limited to handle the complexity of real combat? Share your opinion in the comments below. And if you enjoyed the video, please leave a like, subscribe to the channel, and hit that notification bell for more content. Like today's. Thanks for watching, and we'll see you in the next one.